Tonight's presentation is about the nature of nano, and this is the study of materials at an extremely small level. So these are where materials at that small level, they exhibit sometimes new properties and behaviors, and they have all sorts of applications. I'm not going to get into them. I'll have our two speakers outline some of the technologies and applications that you might actually not know of and might actually use. So the researchers at Argonne in our Center for Nanoscale Materials are creating new materials, methods, and technologies that address some of our nation's greatest challenges in energy security, environmental stewardship, and economic competitiveness. Tonight, Argonne's proud to partner on this event with the Chicago Council on Science and Technology, otherwise known as C2ST. And C2ST is a nonprofit. It's a member-based organization that pulls research and researchers out of the laboratories and bring them out into the public, directly to you. So we applaud that effort, certainly. For tonight, we're pleased to bring you two exciting speakers. One I know very well, Amanda Petford-Long. She is the director of Argonne's Nanoscience and Technology Division, and also the director of the Center for Nanoscale Materials here at Argonne. She has a PhD in materials science from the University of Oxford. She's authored more than 270 scientific papers, which is quite a lot. She's a professor at Northwestern University, where she teaches a graduate course on nanoscale magnetic materials for information storage. Tonight, she will talk about current research efforts and advances in nanotechnology and highlight the societal implications of research that's happening here at the laboratory. Our second speaker is Adam Kahn. Adam is the founder and CEO of AKHAN Technologies, an Illinois-based company that pioneers work in the diamond semiconductor technology space. You may have seen Adam last night on Chicago Tonight. He was being interviewed, and it was a really great interview, and hopefully he'll pick up on that tonight. He's the co-inventor of the Mirage Diamond Platform, which was a 2013 R&D 100 award-winning technology that was developed jointly with Argonne's Center for Nanoscale Materials. We have a close collaboration. He's the winner of the 2013 Midwest Innovation Summit Clean Tech Open Accelerator, and recently was named to Forbes magazine's 30 Under 30 list, which is a tally of the brightest stars in 15 different fields under the age of 30. So tonight, before I, just a little bit on logistics, we're gonna hold the Q&A to the very end. So we'll start with Amanda giving her presentation, move to Adam, and then invite them both up onto the stage to answer your questions. So with that, I'll turn it over to Amanda Petford-Long.
Good evening, everybody, and thank you very much for coming out on this rather cold evening. I hope you all survived the snow. So what I want to do, as Matt has said, is to talk through some of the things that we do at the Center of Nanoscale Materials and a little bit about how that is relevant, I hope, to things in the real world. A lot of what we do is very fundamental science, but a lot of what we do is use-inspired. We're not doing so much applied science ourselves, and Adam is going to follow on and speak about one way in which some of our science has, in fact, spun out into a more applied arena. So I thought I'd start by saying, what is nanotechnology? And it's defined by the Oxford English Dictionary in this way, as you can tell. That's where I grew up, so we have to use that dictionary, I'm afraid. The branch of technology that deals with dimensions and tolerances of 1 to 100 nanometers. Or, more generally, with the manipulation of individual atoms and molecules. And that's the kind of level that we're dealing with, the kind of length scale that we're dealing with. And nanotechnology is really how we make use of nanoscience. And why nanoscience is exciting is because at these small scales, actually totally new properties come out. Materials behave differently. You take a piece of gold, you can make it smaller and smaller and smaller, and it still behaves in a way that we can understand and in a way that's the same as, you know, the gold in your rings behaves. But if we make it very small, it starts to behave differently. And that's what makes it all so exciting. And to give you some idea of the scale, this is a scale bar here from 1 meter down to 1 nanometer. So to put in perspective how small 1 nanometer is, here are some objects that you find at all these different length scales. So from a child here down to the sort of size of a hair, a human hair, it's about a factor of 10,000. If we go down to 10 nanometers, which is about the size of a virus, we're going another factor of 10,000. And really, what we do at the Centre for Nanoscale Materials in Nano is encompassed here, between 100 nanometers down to single atoms. And there's some very cool and interesting things you can do as you go down in size. This is a little race car here that's been printed at the nanoscale, so 200 micron scale. Here's a little snowman that's been made, not of snow, but deposited on the end of a little tip that we actually use to scan over a surface and to understand something about that surface. Here we have a semiconductor nanostructure, part of a device. And then at the very smallest scale here, IBM, written with 35 xenon atoms. Obviously, they don't self-arrange themselves in that, even at the Centre for Nanoscale Materials. We're not that clever. But you can push atoms around and make them assemble that way to really any structure and shape you want. And that's what makes all this so exciting. And, you know, technologically, as we say, it's really small. But I'm always saying, oh, it's about 100 nanometers across. Or it's, you know, everyone else is saying, well, it's very small. But to us, microns are big. And so it's all sort of relative. So I also wanted to pose the question to you, do you actually use nanotechnology? And most likely you do, or at least you've come across it. Band-aids are being sold these days, and actually also socks and other odd things, coated with silver nanoparticles. And it's actually been known for thousands of years that silver is naturally antibacterial. And so it's a very good material to coat onto a Band-aid because it just helps put an antibacterial layer there directly on a wound. Tennis racket here, this one is a nanocomposite, which contains carbon nanotubes, which make it light, but also very strong. This is St. Cecilia from a stained glass window in the cathedral in Oxford. And the colours, the different colours that you see in the stained glass there, arise because there are nanoparticles embedded in the glass. And those nanoparticles that are embedded in the glass actually change the optical properties of the light. They change the wavelength of the light when it goes through the stained glass. And the red colour that you see here in her halo, that arises because of gold nanoparticles. And so that's what I mean in a way that, you know, the properties change totally. You wouldn't expect gold to look red, but in fact, at the scale it does. This is a flexible display here that Samsung is making. And they use quantum dots to generate colour. And what quantum dots are really nanoparticles, so particles at the nanoscale of a semiconductor material. And all these bottles here contain either cadmium selenide or cadmium sulfide quantum dots. Those are two different semiconductors that were made at the CNM. And all those different colours arise simply because of the difference in size of the nanoparticles. So it's a way that we can actually control the properties really very nicely. And then a final example over here, doped titanium, that's titanium oxide nanoparticles. Those are what are in most of the sunscreens that you use and which provide protection from the UV radiation. And in fact, by doping the titanium nanoparticles, you can prevent these free radicals forming, which are what can cause skin damage. And so by controlling the properties of those nanoparticles, we can use them in all sorts of different ways. Of course, there are challenges. It isn't that easy, actually, to do work at this scale. We all stand up and we give these presentations and we say, standard sample looks like this, or you know. This, of course, was something that took us no time at all. And in fact, it's been months and years of people crying in the lab because things are going wrong and not working. But that's what it takes. And the dedication of the scientists that we have at the CNM just makes me very proud to be part of it because they work very, very hard. And they overcome a lot of difficulties to do the research which I'll present to you. And so these are some of the challenges we have to address. How do we predict the behavior? How do we guess? How do we say ahead of time how a material will behave? A lot of that, of course, is done in computers, and we have thanks to fancy computers and very clever people who do theory and modeling. How do we make the nanomaterials? Even if our theorists say, this is the perfect material, and I need you to make it to be this big, and it'll be this shape, and it'll do all these clever things, someone has to then run off to a lab and actually make that material of the size and shape that we need. We need to understand and control the behavior of the nanomaterials. We need to be able to look at their structure and their properties and tie all that together so that we really have a good understanding. And then we have to do actually, which is not trivial, how do we incorporate our nanoparticles or our nanomaterials into a device so that we can use them in an application? We might make them self-assemble, we might make them arrange themselves, we may pattern them. We can put different materials together. If any of you looked at Hongxing Hu's poster, she's doing some very nice work self-assembling different nanoparticles together. Jay was talking about theory, about how she does modeling and theory. And Adina was talking about ways that she looks at materials, that she's also in fact patterning. And so these are all different parts that have to go together in a whole to make up nanoscience. And finally, safe use of nanomaterials. I'm sure you will have heard a lot in the news over the years, are nanomaterials safe or are they not? And of course that's something we take very seriously, something we're involved in at a national level, is understanding nanomaterial safety. So to think about what's being done nationally, there are many and varied potential applications of nanotechnology, and there are new ones coming online all the time. And so governments internationally have invested billions of dollars in science. The European Union, 1.2 billion, Japan, 75 million. And to date, the USA has invested about $3.7 billion. And a lot of that has been through the National Nanoscience Initiative. And the participants in that, we're involved, industry, universities and national labs, and the national funding agencies, such as the Department of Energy and the National Science Fund. But I wanted to sort of drill down now from international, national, how do we get involved here at Argonne? Well, a few years ago, the Department of Energy set up 5 nanoscale science research centres, NSRCs. There are 5 across the country, one at Berkeley, these 2 in Los Alamos and Sandia National Labs in New Mexico, the Centre for Nanophase Material Science at Oak Ridge National Lab in Tennessee, the Centre for Functional Nanomaterials at Brookhaven National Lab on Long Island, and the Centre for Nanoscale Materials here at Argonne, which is attached to the Advanced Photon Source, and you're here in part of that building. And so here at the CNM, we support, as do the other nano centres, basic and applied research. We develop advanced instrumentation, and we help generate new scientific insights, and we create materials with novel properties. But we don't do that in isolation. We don't do it in a vacuum, because we're a user facility. I'll talk a little bit more about what that means, but basically anyone, anywhere in the world, if they have a good idea, they can write a proposal and they can come and work with us here at the CNM. And we have a very strong internal science program of our own, but then staff also spend 50% of their time working with users. And so if I look at the structure of the CNM, we have 6 research groups, about to be 7 actually, because we're adding the Electron Microscopy Centre, and then we have a central facility. And we did this sort of cog schematic on purpose, because each of those different groups is involved in different things. Some have a more emphasis on making materials, others have more emphasis on looking at materials. The theory group obviously does a lot of simulation. And those 6 groups have to work together. And we're working together to solve bigger problems than we could possibly solve if we had each group working individually. And then all of them work together with this user facility, centre here. So if we look at the user centre, access is free. If you have a good idea, you write a proposal, you can come and use everything that we have in the CNM for free. And more than I think than using the tools and the toys that we have, you get access to the very, very clever and talented people that we employ at the CNM who work with users on their projects. We have users from 38 states plus Puerto Rico and a further 20 countries. And for our industrial users, such as Adam, we are probably targeting, for most of them, projects that are a little bit further out in time. So we're not doing, I suppose, service work for industry. We are helping them to develop their new ideas. And I've listed down here some of our recent industrial. This is a map showing where our users come from, with dark blue for any states from which we have users, and then little pins to represent the other countries. And we have quite a spread of users. Our users have increased since we started in 2007. So we're running about 450 users last year, and I would imagine we'll be much the same this year, pretty much capacity. So the Department of Energy runs a lot of user facilities, 13 in all, and the 5 nano centres are a little bit unique in that we make things as well as look at things. I mentioned before, we're here as part of the Advanced Photon Source, and this is a very large X-ray source, and there's a lot of very cool science that goes on here, looking at all kinds of materials on all different scales. We co-manage one beamline with the Advanced Photon Source, and that's the hard X-ray nanoprobe here. And so the focus of our beamline is obviously on looking at materials. But then we make lots of nanoparticles. We make complicated layers where we're controlling each atom that goes down effectively on the surface, pretty much one at a time, so we know exactly where to go. And in that way, we can control the structure. We have a nice clean room where we can pattern structures and do all sort of more deposition. Then we have experimental equipment for optical microscopy, for electron microscopy, scanning probe microscopy, and a supercomputer, a small supercomputer. I don't know if it should be really called a supercomputer, because we've also, of course, got at Argonne the Blue Gene P and the Blue Gene Q, which are real supercomputers, and we make use of those for very big simulations. Users come, as I said, from all over the world, and they come with a range of very exciting nanoscience and nanotechnology problems. But what we do in our own research program is to sort of focus around what we call energy and information transduction. And what I mean by that is that we're trying to understand how energy and information flow through materials. We don't just want to create a material and, oh, exciting, I'll stay over here. We don't just want to make a material and then look at it in its sort of static form. We want to understand what's going to happen if it's going to be reused in the real world. So we need to understand how that energy and information move around in the materials. So we make materials. This is actually a scanning probe microscope image of some particles on the surface. This is a theoretical simulation here of what it would look like if you were inside a particle of silicon that was being compressed from the outside by liquid under high pressure. We visualize, we look at, we try and see how these materials behave. We don't just look at points on the graph. We actually want to take images and spectra and understand how we can make those materials behave in the best way that we can, and to understand their behavior. And then, of course, we manipulate them. We want to be able to control how those materials behave. So we can do things like, for example, having 2 nanoparticles here, which we move closer together. And the little fairy lights here are supposed to be different colours, because, in fact, if you move them closer together, the light that's given out changes colour. So there's a lot that we can do. And what I've tried to go on to do next is choose 6 examples which give some idea of the kind of things we do. And I hope that they will perhaps show you a little bit of what we do, but also stimulate questions and thoughts about other areas that we could also pursue. So the first of these is in catalysis. And really what we mean by a catalyst is something that makes a particular reaction happen, rather than some reaction that we don't want to happen. It could be that we make the reaction happen faster or at lower temperature, but in some way we're controlling that reaction. And the one that we're looking at here, starting with propane, we're all familiar with these from lugging them back and forwards on our decks to our barbecues. And if you react propane, there are three things it could do. It could go to carbon dioxide, lost to the atmosphere. It could go to carbon monoxide, which is highly undesirable and highly toxic. But what we'd like to do with it is we'd like to turn it into propylene feedstock. Propylene is a very widely used material in all sorts of different forms. I'm a climber, so I like polypropylene rope. Polypropylene carpet can be a bit dangerous in the winter when it's very dry and you get static off it. And I'm sure some of you will have sat at O'Hare waiting for your aeroplanes to be de-iced by covering them in this horrible pink goopy propylene glycol. And so what can we do at the CNM to make that particular reaction happen rather than the other ones? Well, some of our theorists got together and they modelled what happened when a propylene molecule up here landed either on a flat metal surface, it could be platinum or silver, versus what happened when that same molecule landed on a small particle here. And what you'll see is that the propylene molecules come down, they lose a hydrogen atom here, and then they kind of sit there and it doesn't look particularly exciting. But what I'd like you to look at is what happens shortly when they feel like it. That one stays there, gets stuck. This one lifts up again. And so now we've taken propane, we've taken that hydrogen off, and we've released the propane back so that now that reaction product can be gathered up and used to make propylene. And the reason that this doesn't work terribly well, it gets stuck here, this is the kind of energy curve. It's a sort of roller coaster that the reaction has to go over. And you can see that very high peak there. And what happens is that the reaction wants to go over that peak and it just gets stuck. There's too much energy that's needed. But here we have this nice roller coaster, the green one, which is what happens on the cluster. We don't need as much energy. And then, having done this in theory, our experimentalists went on to show that, in fact, this is exactly what happened. That you might think is very small, but I would point out to you this slide here, which is a sort of measure of the total US energy usage in terawatts. That's a very big number, 3.5 terawatts. And the amount of energy that gets used to make ethylene and propylene is big enough that it's a visible slice on that pie chart. So by using this different catalyst, we can use a lot less energy to make the propylene. And so that means that we're going to be able to reduce the size of that pie slice. And so that's actually a very important thing to be able to do. So what I want to go on to now are 3 examples of what I've called functional materials and devices. And the first of these is read heads for hard disk drives. You probably all have computers. A lot of them will still have magnetic hard drives. Some of them these days have solid-state drives, but a lot of them will still have hard drives. And if you look at a hard drive, this is a micro drive from Seagate here with a pencil in the background. You can see the disk, and here's the arm. It has the recording head right at the end of it. And you're all arranged on a nice arc here, and the bits of information on a disk are written on arcs around the disk. And if you were all bits of information on a computer disk on a hard drive and you looked up and you looked at the recording head flying over the top of you, that's what you'd see. There's part of the recording head that does the writing, and there's part of the recording head that does the reading. But that's what you'd see if you looked up. And what I'll focus on is the part of the recording head here that does the reading. It's still staggering to me because this is my area of research and I've worked in this for a long time. But you can go to Fry's or Best Buy or somewhere and you can buy a hard drive for $90 that has this huge storage capacity. And it's just incredible because the technology and the nanoscience that's gone into making these is really staggering. And it involves controlling layers, really at the level of a single atom thickness. It's really amazing. And if we focus in on that head, it could have all these different layers in it. There's a magnesium oxide layer here in the middle, and then these layers are cobalt iron with boron of various different compositions. There's a platinum manganese layer down here, that's an antiferromagnet. And there's ruthenium that's used as a capping layer, and also down here as a spacer. And I won't go into a lot of the details of how this works, but every single one of those layers is needed. And every single one of those layers, the thickness has to be controlled, the roughness of the surface, because that changes the properties and it changes the behavior. And so one thing that we went in and looked at was, whoops, I should have explained one thing back here. One thing we went and looked at was why it turned out that the behavior of the devices was better if you had two magnetic layers here, and two layers here, and two layers here, rather than having one layer in each place. One layer in each place would be much easier to make, and so why would you bother to put two? Why would you add in all that extra complexity? So it turns out what we used was called an atom probe tomograph, and what that allows us to do is basically at the atomic scale level identify what the atoms are and where they're sitting in 3 dimensions. And so we can actually go in and kind of count the number of atoms, quite literally, that we have in our sample. And in this case, what we were counting are these blue atoms, the boron atoms, because it turns out that those are actually the ones that really critically control whether a device is good or not, by the way that they move around when you heat the structure up. And in the not so good sample here, which only had 1 layer, there's more boron here than there is in here. The scale is 5 nanometers, and these are literally individual boron atoms. But as you go across that layer, it's not all the same, it varies. And because it varies, the properties are not very good. But put the 2 layers one on top of each other, and it turns out that what happens is it all becomes nice and uniform. And so by imaging the nature and the position of each of these atoms within these complicated layers, we could work back from that to explain and go back to, in this case, we were working with Canon and Elva in Japan, to explain to them why it was that one set of samples worked better than another. And that's just one tiny little contribution, I suppose, to the amazing advances in information technology that we've all seen over the past few years. But actually, nearly all of these advances, as we go up this chart, which is year against gigabits per square inch, that lovely SI unit, my scientific colleagues, all these improvements are a result of very dedicated nanoscience discoveries that have led to these improvements in nanotechnology. So the next type of material I want to talk about is nanobatteries. Batteries are a huge part of all our lives. Can't really get away from them. No matter whether you're trying to drill holes in your wall to put up a picture, or you have one of these very expensive and rather nice motorcycles over here, or electric cars, which of course Argonne's also doing a huge amount of work on. But all these devices rely on batteries, various different types. And the real problem with them is actually shown in this plot here, which plots energy density against power density. And all of these capacitors, batteries, fuel cells are down here. Where we'd like to be is up here, in that corner. Because we want high energy and power density, we don't want to lose capacity loss with time, we want to keep batteries that last a long time. We've all seen the nice little YouTube videos of laptops on fire. And of course, currently they're quite expensive. And so some researchers at the CNM and the Chemical Sciences and Engineering Division here at Argonne came up with the idea of using a mat of titanium oxide nanotubes. So if you look at this, it's literally a lot of little tubes that are all standing up next to each other. They look a bit of a mess, and they're amorphous, they don't have a crystal structure. But what happens is that when you cycle lithium through them, the batteries get better. This is part of a lithium battery. It's the anode for a lithium battery. And normally, of course, as you cycle batteries, you know, they get worse. Well, these get better, which is quite an amazing discovery. And the question is why? And the answer is, if I can get this movie to play again, because of course it was playing while I was talking. Okay, I'll play again. If you look at this, this is the amorphous structure here, so completely random atom arrangement. And what's being simulated here is what happens when the lithium goes into that material. And you can see that as the simulation progresses, so you start to form these lines. And what you finally end up with is a perfectly ordered crystal structure of lithium, titanium, oxygen. And that's what's shown in the simulation here. You're starting with the amorphous random structure, and here it's now perfectly crystalline. And again, by combining experiment and simulation, there was this completely new reaction pathway found, and that will only happen at the nanoscale. You wouldn't see that in a bulk material. And so, by using those titanium oxide nanotubes as the anode, we've been able to put a point over here on that graph. And so we've been able to get a fast charging, discharging battery with a high capacity and a long cycle life. Of course, there's a lot more that has to be done. You know, this is very fundamental studies, and so this has to be now made into a device. But that's all can go forward. And for my last example on functional materials, I wanted to talk about solar cells. And the reason for that is, of course, you know, we are a Department of Energy lab, and we would like to be able to use more efficiently the energy sources that we have available, but also to find new energy sources. And if you look here at the total number of terawatts there that are striking the land and the ocean, it's this very, very large number, 96,000. And even if you thought about the sunlight only landing on the land, it's still 28,000 terawatts. And even if you went down and only covered 2% of the land in solar cells, take it down to 560 terawatts. And then you say, well, we've got a 12% efficiency, 67 terawatts. But that is still more than twice the projected global energy demand for 2050. It's a huge, huge amount of energy up there. And the question is how we can collect that. And if we look at what's available currently, commercial solar cells, I mean, there are lots out there and more people are using them. They're based on silicon or on cadmium telluride or on SiGs, which is copper, indium, gallium selenide. But silicon is expensive to process, and so you have a large investment. Cadmium and tellurium and some of the elements in SiGs are rare, and that's a problem if you're going to run out of the materials. Also, cadmium's actually quite toxic, which again is not ideal. It's still within cadmium telluride, so when it's actually in the solar cell, it's not a problem, but the problem comes at the end of the life of the solar cell when you have to generate the waste materials. And so none of those really fully address what we need for solar energy. And so here at the CNM, we've been working with a group at the University of Chicago who developed a molecule that currently has the highest record for polymer solar cell efficiency. And so we're working on organic photovoltaics, and that's basically solar cells that are based on organic materials because you can make them quickly, low cost, they're flexible, as is shown here. They're very benign to the environment, lightweight, all good things, all very good things. And these organic solar cells that we've been studying here are on the nanoscale. The layers that go into them are about 100 nanometers thick. And even beyond that, within those layers, there's a very complex hierarchical structure. And what I mean by that is, it's ordered at all different length scales. If you home in on the very, very finest length scale, here you've got the molecules, but those molecules arrange themselves into little domains, and then the domains of different types of molecules arrange themselves on a rather larger scale. And then here you've got the sort of two different types of domains here. And if we look at what happens within those domains, the way a solar cell works, light comes in, it generates a pair of charges, one positive, one negative, and then they have to flow and eventually reach the anode and the cathode. Well, if we've got this nice material that's sort of interdigitated, the charges don't have to flow so far, and that makes the material very efficient. And so in that way, we can start in some way to help overcome this problem of the high expense and low efficiency of solar cells. Of course, another way of using sunlight is through photosynthesis, and plants have been doing this for a very long time, and they do it incredibly well. And if you look at how that actually works, this is an image here of a natural photosynthetic bacterium. And within the bacteriochlorophyll, the chlorophyll is the green substance that is what actually collects the energy and also is very popular in all kinds of energy drinks these days. But what that does, it absorbs energy from the sunlight here and it transports it to a reaction center. And the reaction center is where the photocatalytic reactions happen, and that's what powers the bacteria. But what's really critical about this, and what plants over many millennia have learned to do, and we're really only just learning to do, is that those charges flow in a particular direction. They don't get generated in this disk over here and then just kind of whirl around in a circle. They're heading off somewhere, and they know where they're going. And they're all heading off to get into that reaction center. Because if they didn't, they're useless to the plant. So the plant has learned how to do that. And that's one of the tricks that we have to try and work around. And so here at the CNM, we've been working with a group at Northwestern University who have developed these metallo-organic frameworks, or MOFs. And these consist of molecules called porphyrins, which are the analogues of the chlorophyll. And those are all linked together. And they're linked together to form actually quite a rigid structure. I mean, you can pick this stuff up. You know, you can make a sheet of this. This is 500 microns here. That's quite big. It's 0.5 millimeter. And so, they're also very, very light. And I'll explain in a moment how they work. But what's important about being able to make these sheets here is that you can actually incorporate them into a device. They're compatible with all those other materials that you would have in a sort of photoelectrode or some kind of light harvesting device. And the way they work is really rather clever. So sunlight comes in over there, eventually. There we go. And it generates this electron-hole pair, charge, positive, negative charge pair. And that pair of charges moves from one porphyrin to another. And as it moves through, we know it's moving through because each time it emits a very small amount of light, this red light here, and that's what we can detect using one of the optical microscopes, a very special optical microscope that we have at the CNM. What we're interested to know with this is how we can control the direction those charges will flow. And that turns out very cleverly that the charges will move from one flat, the molecules are quite flat, like you can imagine a deck of playing cards really. The charge moves from one playing card surface to the next. It very rarely moves sideways. And so with this very clever structure, we've now managed to control the direction in which the charge will flow. So the next challenge was to say, okay, well, we know how the charge is flowing, the direction, but how far is it going? Well, we could tell that as well by putting in, every so often, these molecules which actually absorbed the charge and stopped them flowing any further. And so you put in lots of those molecules and you say, okay, well, the charge gets to it and then it stops. Well, supposing I move it 10 porphyrins further down, can the charge still get there? Move it another 10 down, can it still get there? And that's the way of testing how far the charge will flow. And in fact, the charge will migrate up to 90 porphyrin struts. May not sound very far, but honestly, that's far enough that you could actually now use this in a device, particularly if you can work out ways, as I showed before, of forming some sort of nanostructure where you'd have your metal organic framework here in the middle, and there are your anode and your cathode on either side. And so this is a route to integrate light harvesting components into solar energy devices in a very clever way. So the final example I want to show is, I feel I should say now for something completely different, because I'm going to get away now from sort of new technologies and actually show you how nanoscience can be used to look at rather an old problem. And that's using our hard X-ray nanoprobe. This is a very advanced and very complicated tool. But what it has been applied to in this particular example is looking at paint in some of Pablo Picasso's paintings. And this is a project that the CNM has done in collaboration with the Art Institute in Chicago, who were lucky enough to be allowed to scrape off some tiny, tiny amounts off a Picasso painting, presumably somewhere down in a corner where nobody would notice, in order to try and understand what type of paints Picasso used. Because there's been a debate, and it was thought that he probably used house paint. He didn't actually use artist's paint for a lot of his paintings, he used house paint. And in particular, ones from Ripalin, which was a factory company in France at the time that he was painting. And I was absolutely fascinated to discover that the Art Institute has an archive of paints. So they have artists' paints, house paints from all over the world, going back really a very long time. So what they were able to do was to provide us with samples of these different paints that we could then look at and compare with the paint from Picasso's painting. You may be thinking to yourself, what on earth has that got to do with nanoparticles? So it's actually very, very cool. I was really fascinated by this. So if you think of paint, it involves all sorts of different additives, pigments, a solvent, a binder, and a lot of those that are on a very large scale. At the macro scale, you know, there's a tube of paint, and there are very easy techniques you can use to say what elements in the periodic table are in the paint, and that's fine. At the microscopic scale, well, you might look at what the paint looks like. You get the little flakes of paint, and you can analyze those flakes. But it turns out that in order to actually distinguish the different paints, you have to go much smaller than the microscale. You have to go down to the nanoscale. And so what we did was use a technique called X-ray fluorescence, which will tell you not only what elements are present, but also how they're distributed in a piece of material. And we use that to look at the paint flakes. And so if we look at, and the paint that was looked at was white paint, and the pigment that's in white paint is zinc oxide. And so yes, we're going to see zinc and we're going to see oxygen there. But what distinguished them are very small trace amounts of different elements, such as, for example, lead or titanium, iron. And those are distributed differently in the different types of paint flakes. If we look at the Ripalin paint or the artist's paint, you can see zinc everywhere because it's zinc oxide. I'd hope you'd see that. But if you look at how the iron is distributed, or how the titanium is distributed, or how the lead is distributed, the kind of scale, the size of the features and how far apart they are is different between the two. And so by looking at that and by then comparing with this little tiny flake of paint that came from somewhere over here on this painting, we were able to compare the distribution of the elements in that paint with these two types of paint. And what it turns out is that, in fact, house paints to paint both the painting in the previous slide and also this painting here, the red armchair. And that's Volker Rose from CNM and Francesca Casadio from the Art Institute. So I rather rudely said he used common house paint here. That seems a bit unfair. Of course, what he did with the house paint is totally amazing and far beyond anything I could even consider. But I thought that this was a rather nice contrast from some of the sort of high technology examples. We use a very high technology tool. We use the whole of this vast synchrotron here and this very complex piece of material to look at this very small flake of paint. So going forward, what do we want to do next? What we want to do next is increase complexity. We can make single nanoparticles. We can understand what they do. We're starting to be able to put them together, different types of nanoparticles, different types of nanostructures. And really, I would classify this that in medieval times, you know, we've gone from nanotechnology by chance Nobody knew what the optical properties of gold nanoparticles were. It just happened that they discovered these amazing properties. To now nanotechnology by design, where we're combining different functionalities and different materials. And that is such a rich, huge field. There's still an awful lot to do. So we'll keep working on it, which is good. So I'd like to make some acknowledgements, firstly to the staff at the CNM, both because they're wonderful people to work with, very, very talented, but also because they were kind enough to contribute slides, and it's always helpful. Also to our colleagues outside Argonne, to our users who have faith in us and who come and work here at CNM, and to our collaborators. To our funding sources, we're mainly funded by the Department of Energy. And we made use of some other user facilities, the Electron Microscopy Centre and the Advanced Photon Source. And again, I would like to take this opportunity to thank you for coming to listen. And I'll hand over to Adam Khan.
Thank you. It's my privilege and honor to be here with you this evening, talking about my favorite subject, nanodiamond. And now that the polar vortex has left us, we can tune our focus away from the prospect of a new ice age to the prospect of a new diamond age. And it's a very interesting topic. It's one I get very excited talking about. And honestly, in my work, I do a lot of business and a lot of technology, but really nothing excites me more than the science behind it all. And when I was initially approached about discussing the nanodiamond work that we're doing in the first Nature of Nano presentation, I had initially thought, this is a really good opportunity to engage with the broader Chicagoland area and really show them the exciting work that's happening right here in their backyard. When approached to talk about this evening's talk, the Nature of Nano 2, I thought, wow, that's even more interesting because Nature of Nano 2 sounds more like a sequel, like there's unfinished business. And as it turns out, there really is, because in December, we had this conversation about nanodiamond, how it's going to change the semiconductor world, how the problems in silicon aren't necessarily incumbent upon diamond. And then a month later, oh, excuse me. Sorry, I jumped right into my presentation here. A month later, President Obama actually made an announcement that wide bandgap semiconductor technology is an imperative need domestically, that silicon chips were reaching the limitations of their power conversions, and that wide bandgap semiconductors had the possibility to operate at higher frequencies, temperatures, and voltages, and could eliminate up to 90% of these inefficiencies. But one important detail left out in that study is that diamond is the ultimate wide bandgap semiconducting material by orders of magnitude. So we retune our focus from the initial talk to focus on power electronics and diamond within that context. So semiconductors are ubiquitous in application. They're found virtually everywhere in our day-to-day lives. If a device has a power source, the chances are there's a semiconductor component in it. And they do all sorts of novel things like amplify, switch, or convert energy inputs, driving your speaker systems in your music, your car, your washer and dryer, your refrigerator, medical technology, just to name very simply few. But one very unique and very novel attribute of semiconductors is that you can change the conductivity by the addition of these foreign atoms through a process called doping. And if we take a step back and we think of the semiconductor world in a dollar and cents standpoint, we see that actually about 1/3 of the global GDP is driven directly by the semiconductor industry. We count not the materials and the equipment, but also the people it employs, the jobs, the intellectual property, and so on. That's a very, very large and significant component. Actually, the largest component, the US manufacturing capability. And today, about 95 or over 95% of these devices are fabricated on silicon. But in the beginning, it didn't start with silicon. It actually began with germanium. Actually, in the beginning, semiconductors were thought to be useless because they were so erratic and uncontrollable. But as the theory evolved, bandgap theory, we actually found that, wow, semiconductors have very, very novel properties that actually make life far more simple for us. So silicon, as I mentioned in the beginning, was believed to be too expensive. It required very, very high temperatures to be processed. It was very costly, despite it being derived from sand. So germanium was the material of choice. But when incorporating this germanium technology in products like a germanium transistor radio, it was found that if your car was parked outside on a very hot day, and you came back to your car and turned on the radio, it no longer worked. Now, why is that? Well, as it turns out, germanium is not very heat efficient. Actually, it operates at about 85 degrees C optimally. And above that, it reverts to intrinsic use. So there was a strong motivation to switch away from germanium and over to silicon, which could operate at much higher temperatures, 175 degrees C. So the move to silicon happened very, very abruptly in the 1960s. Over the course of just a few years, silicon was virtually everywhere in this technology. And so silicon actually has superior electrical capability because it has smaller interatomic spacing. The group 4 elements, carbon, silicon, and germanium, all crystallize in what's called the diamond lattice structure. And germanium, the atoms of germanium are actually a little bit further spaced than they are in silicon. And what that allows in silicon is that the properties can actually become more thermally efficient than germanium because it requires more energy to excite these electrons away from their valence state. And this actually fueled the modern, what we call the computer age, but I like to call the modern electronics age, because it allowed the creation of more and more complex systems. If we remember, computers used to occupy entire rooms, and now we complain that they are heavy in our laps. But the most, I think the most convincing issue of this, or most convincing version of this, is that in the modern cell phone, if we remember the 1980s, the Motorola brick phone had two functions, to call and to receive calls. Today, actually, there's so much more functionality. And we can see on the circuit boards, there's even more complex circuits involved here because we have cameras, we have Wi-Fi, we have GPS, we have video. So infinitely more complex. But now we're at the standpoint where a problem has arisen because we're now accomplishing more circuitry in much tighter profiles. So now thermal management is a major issue in modern electronics. And I like to use the example of the iPad because it's the one that most recently exploded in the Apple Store. But a lot of people have noticed this, that if you keep it in your lap, it's very warm. Or if you use your cell phone for a very short duration, it's very hot to the touch. And this is because the thermal management is such an issue, because silicon is very, very heat inefficient. But beyond that, we have issues with the status quo cooling, where in data centers and computing, of approximately the 120 billion kilowatt hours of electricity consumed worldwide, 50% of that roughly goes just to cooling. And the two options we have predominantly are either convection-based cooling, which is bulky, inefficient, and not easily recycled, or we have these cooling options in packaging where we're incorporating metals in tighter profiles, but with very incremental improvement in the thermal capability. But above and beyond that, electronics waste, or e-waste, is actually a major, major issue. During the last talk, I'd mentioned that it's approximately 50 million tons each year of this electronic waste is produced. But actually, a new report by the UN is forecasting that it's about to increase to 72 million tons. And to contextualize this, this is roughly the weight of the Empire State Building that we're producing in electronic waste each and every year. And what's worse, only about 15% of that is recycled. The rest of it is incinerated, creating greenhouse gases, toxic pollutants, cadmium, lead, etc. And these pollutants don't stay stationary. They float up into the jet stream, they're carried around the world, and it's a global issue. So in terms of the performance, there's a critical need. In terms of the cost, there's a critical need. And in terms of the environmental and sustainability standpoint, there is a critical need. So one such material, which has long been held as a successor technology to silicon potentially, is diamond, because diamond can operate at much higher temperatures than silicon, over 600 degrees C. Diamond's performance does not degrade. It conducts heat approximately 22 times better than that of silicon, over 5 times better than that of copper. But even more important, it's highly enabling for power electronics, where we have superior performance as compared to silicon. We can drive it at higher frequencies. We can switch very quickly, much higher loads of power. And we can do that utilizing thinner and smaller layers and feature sizes as compared to the silicon counterpart for the equating functionality. And here we compare diamond to the other wide band gap materials. And we can see diamond is far superior as compared to even gallium nitride, which is seeing more increased use in the marketplace. And in terms of the material thickness, far less diamond is required to isolate large voltage as compared to the other materials, and especially as compared to silicon. But the concept of diamond is not a new concept. It's been around for some time. All the way back to 1955, when GE pioneered the first high-pressure, high-temperature reactor, where we had a two-story system, occupied a room, and using tremendous loads of pressure, was able to make this synthetic diamond. More recently, in 2003, due to the excitement and the onset of the chemical vapor deposition technology, the diamond age was again resurrected. But here we are 10 years later, and we still don't have diamond everywhere in the marketplace, so we have to ask, where are the diamond electronics? So technology proceeds in what we like to call the technology hype cycle, where there's an initial technology trigger. In this case, we could treat that as the 1955 technology trigger. And there's a peak of inflated expectations. And I would call a Wired magazine article saying the new diamond age inflated expectations, because very shortly after, not much happened. So that's what we call the trough of disillusionment, where certain things are barring the technology from enjoying widespread use. So an interesting study that was actually conducted by the Department of Energy, or more specifically by Argonne National Laboratory, compared all of the wide bandgap semiconductors against that of silicon, specifically for the use of power electronics. And what the report concluded was that diamond shows the best theoretical performance, exceeding every other material by orders of magnitude and figure of merit, but its processing problems have not yet been solved. Diamond is a harder material and it needs even higher temperature for processing, meaning that diamond had to be deposed at over 700 degrees Celsius, which, incorporating that with silicon electronics, would fry the underlying circuitry. So we turned to the biggest market user of silicon, Intel, to see what their opinion would be, because obviously they have the biggest stakeholder in semiconductor. And what they said was that diamond represents a seismic change in semiconductors, where it takes roughly 10 years to evaluate a new material, and there's been a tremendous amount of investment in silicon, and they're not about to abandon that. So how do we take it from the trough of disillusionment to the plateau of productivity? Essentially, there's two things that need to have been done in diamond, and that is to lower the processing temperatures to allow it to be CMOS compatible, or at a low enough temperature where it can be incorporated with silicon technology and process technology. And N-type doping in diamond has been a major issue, where we can't make diamond conduct in a way that would allow you to shift away from the silicon technology and allow you to further this device development. So Argonne has actually played a very pivotal role in the diamond world. And as Amanda mentioned, it's one of the 5 Department of Energy Nano Labs. But what's unique about CNM is it has the expertise in carbon materials, diamond, graphene, carbon nanotubes. So it has not only the equipment sets to uniquely process this material, but it has the in-house expertise, world-class researchers that are working day in and day out, evaluating these materials, working out the kinks and bringing it into the marketplace for industrial users. And their pioneering work in 2003 actually produced nanocrystalline diamond, or diamond on silicon technology, which for the first time we can now incorporate diamond on silicon where we didn't have to have an entire diamond substrate. So the cost was removed from it, and we can actually do it in a larger area. But again, temperature was the issue. So if we fast forward a few years later, CNM actually introduced in 2010 a low temperature diamond deposition method, where now we can depose diamond at 400 degrees C. Which was a breakthrough. So the main problem, N-type doping, remained. And in previous demonstrations of N-type doping, we saw that incorporating these foreign atoms inside of the diamond structure, something very problematic happened. We have crystallographic dislocation. And if we think about this analogously to driving a car down a road, we think about this as like a pothole, because as we know, the conductivity is the product of not only the electron concentration, but also how fast these carriers can move within the material. So if we're trying to think about diamond and the use of electronics, not only is it an issue from a conduction standpoint, but having these potholes also makes it very hard to have smooth contacts for metallization and the like. But in 2013, a new doping technique was shown that utilizing that same single crystal material under the same magnification, incorporating the same amount of impurity atoms, we see no crystallographic dislocation. And this has been our work with Argonne National Laboratory, where initially my company, AKHAN Technologies, performed the initial research and development at Stanford NanoFab. But in June of 2012, we actually began collaborating with the CNM under what's called a rapid access proposal, where we wanted very quickly to bring our materials in and to see all of the neat things going on in there. So I actually had the privilege and honor of working with an expert in the carbon materials world, Dr. Ani Sumant. And a few months later, we were successfully able to combine this N-type process with a low-temperature diamond deposition process. And shortly after that, we began jointly developing this technology under the Cooperative Research and Development Agreement. And if we look very closely at the nano level, we don't see these pits of these crystallographic dislocation sites. We actually see protruding aggregates, which were not shown to be adverse to the electronic characteristics. And shortly after making these announcements, we actually won an R&D 100 award on this technology. So we debuted the Mirage Diamond platform, which combined these two novel features, where we can put diamond down at very low temperatures, not only on silicon, but also on these other wide bandgap materials like gallium nitride, like silicon carbide and the like. And we're actually able to make semiconductor devices from the diamond layer on top. And now, instead of having these systems, which are very, very large and would never fly in a commercial sense, we actually have very compact systems, like the MPCVD Lambda reactor they have at CNM, which is fully automated. So we now have a commercially feasible way of producing these materials. So we looked at the material perspective, and we saw that there was this difference from a phase standpoint. But comparing an actually produced product, like a PIN diode, we had the ability to compare it not only to what's been done previously in diamond, but also the state-of-the-art in silicon technology. And we noticed some very, very interesting things. Not only were we able to produce much higher current density as compared to both silicon technology and the single crystal diamond, where as compared to the diamond world, single crystal diamond technology, we were able to produce over 200 times higher current density and over 1 million times higher current density than that of silicon. But we were able to accomplish this using much thinner layers of diamond. So now things like cost became mitigated. So that's why I started the talk by saying we can turn to the prospect of the dawn of a diamond age, because by combining these components like diodes and transistors, we can make ever more complex systems. For example, a diode and a transistor produces a power inverter for things like uninterruptible power sources, or in forward-looking applications like hybrid electronic vehicles. But we also now have on the prospect of the horizon this technology for faster supercomputers, advanced radar, telecom, and aerospace, and in addition to far more forward-looking applications like MEMS and NEMS. So I want to thank you for your attention. And again, all of the data points that you saw here was a result of the work done with the Center for Nanoscale Materials with my colleague, Dr. Ani Sumant. And because we live in Chicago and because we have this love for diamond, I actually also wanted to mention that in the summer, we're hosting the 2014 New Diamond and Nanocarbon Conference here in Chicago at the Hyatt Regency. Thank you very much.
Answer some questions that you might have. There's the mic. So if you just raise your hand if you have a question, and someone will bring a mic to you. Here we go.
What about this issue of Moore's law? In a few years, we're going to meet the limits. What about this diamond business? Is that going to hit the same restrictions?
So it's interesting, actually. Moore's law, that's a subject for just the computational aspects of it, and I purposefully avoided in it because I didn't want us to just focus on computing. It's a very specific application, and while silicon has been plagued by this issue of Moore's law, diamond does have a resolution to it, but diamond actually can be driven at much higher frequencies using much larger feature sizes comparatively. So it would certainly extend Moore's law, but the problem there is we have to have very large area silicon, right? And that's how we make these devices very cheap. Diamond, however, in large area has not been sufficiently developed at this point. So in the future, absolutely, but I think it makes more sense from a roadmap standpoint to focus on power electronics.
Other questions?
Do you use the diamonds that you put on the drill bits and and then there's the man-made diamonds. Which would be better suited?
So actually, what I like about synthetic diamond is we like to tout that we've actually improved upon Mother Nature, and I don't say that quite slightly, but actually the synthetic diamond is, from an atomic and crystalline perspective, more perfect than the natural diamond. Natural diamond has these colorations because of impurities that are sitting adjacent to the actual seed. So from a performance standpoint, there's very, very little difference between synthetic diamond and natural diamond. But from a humanitarian aspect, we can say that synthetic diamond is obviously conflict and blood-free. So we prefer to use that.
Thanks. So, I mean, I've been following the nano science thing over many years, and I think probably, 10 years ago, it was going to be the next big thing. So you see the graph going up in the early part of the 21st century. I suppose in the education business that I'm involved in, we're interested in, I suppose, educating the workforce that's going to be part of that next big thing. Do you have anything to say, like, is the progress going as we would have hoped? Can we expect a large explosion in employment in this area? Because this is one of the greatest areas in nanotechnology in the whole world, I would say.
Indeed, indeed. And what I love about technology is it's not a linear growth, it's an exponential growth. Things happen very quickly when they do happen. And so it is very vital to be educated and to be trained in this particular segment because it is going to become ever more important. But I think Argonne and the C2West here are doing a terrific job in their outreach and explaining the importance of that, working with the general public. And I'd also like to say that I think that's going to become an important model moving forward. Small business working with national laboratories, because here you have young people like myself with bright ideas. You have seasoned experts, world-renowned experts with unique equipment sets. Together, you can do something useful. And as Amanda mentioned, the national laboratories don't charge you to utilize these facilities if you're publishing this information. So it's very helpful both from a validation and fabrication standpoint.
If I could just make a comment there as well. I think we're trying, no, that was, thank you. I mean, we do a lot of outreach trying to bring in students. I'm showing a video back there. I mean, our youngest users at Argonne are from high school level. And there's a lot of interest around Chicago in getting high school students and even middle school students involved in nano activities because it is an area of growth. And if we can get people interested in it at a very early age, they can do an undergraduate degree in whatever it might be, physics, materials. And there are a lot more graduate courses being offered actually in nanoscience now, nanotechnology. And as far as I know, certainly from my colleagues in the universities, the people that come out from those are not having problems finding jobs.
This is a question for Adam. Are you actually, or your company, actually making and selling any diamond chip products now?
So yes, actually, we have two aspects of what we do. One is called licensing, where we license the technology to existing stakeholders, like aerospace concerns. Now we're actually moving to produce these and actually have fabricational equipment capabilities, actually make finished devices. So that's what we're working on now. Over the next 12 to 18 months, we actually plan to have this product and technology available in the open marketplace. From a licensing standpoint, it's being used, but not from, we're not producing it at this point yet for the broader market.
This question is for Amanda. You mentioned organic photovoltaics. What are your visions for the future in terms of energy usage and eliminating fossil fuels in that respect?
That's a very good question. I mean, I think I would say the organic photovoltaics is one area that's going to be very important, but things like artificial photosynthesis as well, because any way in which we can harness the sun's energy is going to help reduce our reliance on fossil fuels. But I would have to say that going along with looking at new types, new ways of harnessing the energy that's available, we also have to find ways of storing it and of having it available to us at times when we actually need the energy. And so doing the sort of battery and fuel cell development in parallel with that is critically important. And of course, also looking for things like energy efficiency. I mean, Adam's talking about ways in which we can use a lot less energy in our semiconductor devices, and looking at ways of conserving energy so that the energy need is lower is also really critical.
I had a question. With the new diamond technology coming out to control thermal management, would it decrease the need to have internal fans and computer cooling systems?
Absolutely, yeah. That's our major focus from the e-waste and environmental standpoint. That diamond, because it's directly interacting with these materials, is far more thermally effective than these fans which sit adjacent to it. And because the plastics aren't involved, it's much more eco-friendly.
Hold on.
Well, I was wondering about works that high school students could have some kind of opportunity to work at CNM to learn more about the projects. What kind of opportunities are there to work there?
So we have high school students currently coming from IMSA, the Illinois Math and Science Academy, and we have 2 students from there who come currently. They come every Wednesday afternoon for basically pretty much a whole high school year. They're involved in experiments. There's Ralu. There she is. Ralu Devan over there works with one of the students, Dan. And so, he's in there in the lab doing experiments and working with her. And we'd welcome other people doing that. We have other outreach programs that we do where we have, because of the nature of the kind of research that's going on, we do have, and this is a government lab, we have some age restrictions in terms of what we can let people do, just because some things are more dangerous than others, and we have to be aware of everybody's safety. But we do have other opportunities where we have larger groups of students who come and visit the CNM to see what kind of things we do. So, if you're interested, we'd very much welcome that.
Okay, I think we should have one final question, so here we go.
I have a question for Amanda, who is also teaching this nanoscience. So, while, as you said, nanoscience involves and evolves towards complexity. So, what do you see the challenges for teaching this complexity and giving it to other generations?
Thank you. I think, so it is very complex, and I think the issue in trying to teach that is to get across, and I think I'd honestly say this is the same for doing any science teaching. I've taught physics and things for a long time. The difficulty is getting the excitement across while still having to keep the rigor there. You couldn't develop semiconductor devices without maths. I mean, math is involved in that, and I have 2 kids, and when my daughter was about 12, I suppose, she was sort of throwing her hissy fits about trying to do her math homework. I took her iPod and said, see this? A lot of math goes into that. So it's that thing of trying to keep the real excitement and yet get across the fundamental science that has to be understood as well. And I think that's true no matter whether it's nanoscience based on biology or chemistry or physics. That it is just so exciting and so amazing, but there is a certain level of knowledge that you're going to have if you're going to work in that field. And it's trying to get over that sort of barrier to see the excitement, but still understand that you have to, you have to work at it. So it's always, to me, it's also, I would have to say, putting it in context. I've always been driven by nanoscience that's going to spin out into nanotechnology. Even if I don't work on the devices myself, I want to work on the physics that controls the devices. And so always putting it in the context of, I'm teaching you this piece of physics because it's going to help you down the line understand what materials you could choose for a hard drive or what materials you might choose for a organic photovoltaic. So to me, that's an important aspect of the teaching too.
Great, thank you for coming, and thank our speakers for an engaging evening.